So yesterday we heard from Omar Shields talking about factors that affect habitability, and Dave Catling talked about how life can make an impact on its environment that might potentially be measurable. And so today I'm going to talk about the sort of specific things we might want to measure to determine whether or not a planet is habitable or has life on it. And I'm going to look at sort of some measurements that we could take before we go, and then other things that might only be possible when we're actually in the planetary system. So as Omar showed, this is a slightly more sophisticated but no less terrifying diagram about all of the factors that affect the habitability of a planet. And the main takeaway point from this diagram is that for a planet to have liquid water on its surface, it's not just enough to understand the characteristics of the planet, although they're obviously important, but to also understand how that planet interacts with its parent star and with other planets in the system. And so we do a habitability assessment. All of these factors need to be taken into account when making that assessment. So we not only observe the planet, we also want to observe the planetary system and the star. So let's look a little bit at Proxima Cen-b in particular. It's in the habitable zone now, but it was not always in the habitable zone. And so I'm going to describe what might have happened to this planet, and that will motivate the sort of measurements that we want to make in future. So it's orbiting an M-dwarf star, and these stars are superluminous when they are young. And so any star that forms in what becomes the habitable zone when the star is in the main sequence is subjected to very high levels of radiation early on. So that can result in the loss of oceans of water, and via photolysis, the loss of hydrogen, and then a buildup potentially of oxygen in the atmosphere. How much oxygen remains over the 5 billion years of this planet's existence is a question that we're still studying with models and experiments to try and understand how that oxygen might get lost via atmospheric escape or sequestered somehow into the surface and crust. But nonetheless, it's highly likely that, in fact, these planets will have a large amount of oxygen in their atmospheres. So we did work that was led by Rory Barnes, who's here. You can maybe get to talk to him later, looking at sort of stellar evolution and what that might do to the planet. And the net result of that paper was that the answer is, of course, that water may or may not survive depending on the initial conditions. And what we modeled was basically the initial volatile abundance of the planet and also whether or not it had a protective hydrogen envelope. And the conclusion we came to is that if Proxima Centauri formed where it is today, in situ, then it likely lost all of its water. It would have had to have a very large endowment of water to have retained any. But if it migrated in, or if it formed in situ with a 1% hydrogen envelope, it might have been able to protect itself from the loss of volatiles. So this planet could potentially be habitable, which is a result that was also found in the Rebus et al. Paper. So if that planet loses its water and is desiccated, it may have a lot of oxygen, but what will probably happen over time is that it will also build up carbon dioxide in its atmosphere, very much as Venus has today. So as water is lost, plate tectonics is shut down, you no longer have an ocean in which to dissolve carbon dioxide, and so those two sinks of carbon dioxide are lost, and so you can tend to build up CO2 in the atmosphere. And this is what happened to Venus, and I like to think of Venus as kind of the popcorn of the solar system, because if the Earth is like a kernel of corn, Venus has been changed, transitioned into a very different type of atmosphere that it may be very difficult to recover from. So we then have some plausible ideas of what the composition of Proxima Cen-b may be like if it is terrestrial, oxygen-rich, evolving to CO2-rich as the oxygen is sequestered and the CO2 is outgassed. So we took these evolutionary states, and then we put them through coupled climate photochemical models that looked at the incoming spectrum of Proxima Centauri. We got a spectrum of Proxima Centauri with the ultraviolet. And we looked at, for these different types of plausible compositions, oxygen-rich, CO2-rich, or even nitrogen-rich, we imagined that we had migrated something in that was volatile-rich but had a protective hydrogen envelope, so we ended up with something much more Earth-like. If we look at these different environments, calculate how the spectrum of the star changes the composition of the atmosphere and then the resulting climate that comes from that composition, you find that even though Proxima Centauri, it's the same planet, it's sitting at exactly the same position, but depending on its evolutionary history and the composition of the atmosphere that results, you can end up with temperatures going from anywhere from 254 Kelvin, probably too cold for habitability, and desiccated as well, all the way up to 640 Kelvin if it has a very CO2-rich atmosphere. And again, this planet is sitting in the habitable zone. So I think I want to stress here that evolution matters. What happens to the planet matters, and the habitable zone is defined for a planet with an Earth-like atmosphere. If that planet does not have an Earth-like atmosphere, then it's not necessarily habitable within the habitable zone. But we've certainly found several scenarios where the planet is potentially habitable. But with a nod to Dimitar, For the high O2 atmosphere, where water was actually retained, maybe that might be okay for life, but maybe it's not a great place, for example, for the origin of life. Okay, so we looked at these different compositions. And so now we ask ourselves, okay, so there could be a diversity of different types of terrestrial environments there. How do we tell, in fact, if the planet is habitable? So going back very much to basics, the first thing we want to do is confirm the presence and nature of the atmosphere. Does it have one? And what is it made of? We want to try and directly detect surface liquid water, if we possibly can. And we also want to characterize the planetary environment in general. So, for example, look for a census of greenhouse gases that could be important in telling us what the climate is like. So for looking for the presence of a terrestrial atmosphere, this is something we might be able to do in the short term. It could be a very challenging observation. But if we would use broadband Miri imaging and to get thermal phase curves of the planet, and here we show a simulation of one of our self-consistent environments. This is the Earth-like planet. And you can see the deviation from the blackbody curve into the CO2 band here. That deviation is what we're trying to measure to actually potentially detect carbon dioxide. And we can detect this if there is a day-night temperature difference on the planet. And the strength of that signal will be a function of the day-night temperature difference. So if there's a very small temperature difference, which is what we'd actually expect from a more habitable planet, it will ironically be harder to detect that CO2. If there's a very high temperature difference, the signal will be larger. But we're still looking at signals that are potentially possible, but challenging, maybe with JWST. So that's something we could go after initially. The other thing we might try to do is map the planetary surface. To do this, we would need direct imaging observations to be able to see reflected light from the target. These are observations of the Earth taken by the EPOXI spacecraft. We essentially studied Earth as if it were an exoplanet, looking at the Earth as seeing light curves in different wavelengths of light, putting all of those together and using inversion techniques a little bit like the ones that Svetlana described yesterday to, in fact, pull out knowledge. And this was just from a single day of observation. So sampled once every hour, a single day of observation to pull out a map of what the Earth was like as far as being able to see areas where oceans and continents might, in fact, exist. We can also look as a function of phase as well. So the Earth not only has diurnal differences, but also phase differences. And the interesting thing about this diagram is the behavior as a function of wavelength as the planet goes through full phases. So full phase here towards crescent. You can see at the shorter wavelengths that, in fact, it drops off very evenly as you go towards crescent phase. But at the longer wavelengths, you can see this flattening off. That can be due to longer path lengths in the atmosphere, the forward scattering of clouds, or something else far more intriguing, which is in fact glint from an ocean. And so here's two examples of glint in the solar system, one taken from Titan, which you can see glint off an ethane lake here. I think it's Kraken Mare near the North Pole. And then on the Earth here, this is another experiment taken by the L-CROSS spacecraft as it flew by the Earth on its way to a fiery death on the surface of the moon. And that one, if you look at the crescent phase, can you see the little circle of light that sits in the middle of that crescent phase? If so, you have become a remote sensing ocean detector, because that is, in fact, the glint coming off of the Earth. And so for typical exoplanet observations, we would need to sort of fold that down into photometry and look at the behavior of that falling off of the light as you go towards crescent phase. But if we were in the Proxima Centauri system, we could try to image this directly. And in fact, those L-CROSS images might look something like the sorts of things we might pick up in a single filter. So can we detect glint for Proxima b from JWST? The answer is a resounding no. We would need sort of a 1 part in 10 to the 8 stability in our light curve, which we're unlikely to achieve. We need something more like 10 parts per million. So it's highly unlikely we'll be able to do this, in fact, with JWST for Proxima Cen. However, upcoming missions, they will have that stability and contrast, but their problem will be the angular separation of the planet from the star. And so to get to the crescent phase, we need this phase of about 150 degrees, which is where the discrepancy between forward scattering from clouds and the ocean can, in fact, be pulled out of a realistic Earth. And so we're looking at potentially 1.5 lambda over d for a 16-meter telescope, down to about 3 lambda over d for 30 meters on the ground. So this is something we could potentially look at. And 16 meters is the current largest example that we're studying for the LUVOIR Space Telescope. Or we could use a flyby if we're actually in this system. Not to be left out, we looked at this also for Alpha Centauri, where it's much easier to actually angularly separate a planet in the habitable zone. And this was a simulation we did for the EXO-C spacecraft, a 1.4 meter moderate probe class, where we looked at roughly about 20 days to potentially look at 2 phases and to look for glint from a planet orbiting Alpha Centauri. Another thing we could look for is geological activity. So if we had images in the near-infrared or mid-infrared, and I was super excited to see that Phil's chip might potentially have those sorts of capabilities, then we could look for anomalies in the thermal radiation that are due to volcanic eruptions on the surface, which would be interesting to see. I'm showing this example. This is actually something taken from my thesis. Finally, it's useful. So basically, this is spectral mapping of the night side of Venus looking down at what we call atmospheric windows between strong carbon dioxide and water bands where we can see all the way to the surface. And this dark circle you hear is less radiation coming from the cold top of a shield volcano. That's Beta Regio sitting over here and Phoebe Regio down here. And so you can actually image the surface. If we were to see an anomalous bright spot on that volcano, especially if it was temporally variable, then that might indicate that we're seeing geological activity. Other things we could do, of course, is also potentially look for time-dependent aerosols or injections of things that come from volcanoes, especially localized things like carbon dioxide, sulfur dioxide, and even water vapor coming from the surface that might indicate volcanic activity. Another thing we could go after, even before we get there, potentially is looking for exo-aurorae and air glow on the planet. So we looked for Proxima Cen B, and this is a paper led by 2 of our students, Jake Lustig-Jaeger and Rodrigo Luger. And what they looked at was actually looking in the discovery data of Proxima Cen B, looking to see if they could, in fact, detect the oxygen green line. And this is because, of course, the star is very active, and they did the calculations to show that the aurora power would probably be about 100 times stronger than on Earth, but they were not able to find it in the discovery data. But if there was more magnetospheric activity, and also if we could get sort of a coronagraph and a high-res spectrograph on the ELTs, this is something we could also potentially go and look for. And I'm also pointing out here, Venus also shows air glow. This is from molecular oxygen in the atmosphere, which looks like this in high res, but you get these beautiful patterns showing essentially that this atmosphere contains oxygen of some sort. In this case, it's from carbon dioxide photolysis. So in searching for life, just as we finish up here, again, I love oxygen. It is a very interesting molecule to look for simply because it belongs to what I would call the metabolic winners on this planet, the metabolism that managed to harvest the light from the sun. That gave, and uses water and carbon dioxide. It was able to spread over the surface of the planet, manifest destiny, and to essentially dominate the environment of our planet. And so when we're trying to look at things from a distance or trying to look at the first things that we can see, we want to see these very, very strong signals. Oxygen, however, does have these false positives that we've identified. So essentially, I won't go into all the details, but there are ways that stars, and especially M dwarfs, can split up carbon dioxide and water vapor and end up with stable oxygen in the atmosphere as a result of these processes. And so there are things we need to look for to try and discriminate whether or not those processes are going on rather than photosynthesis. So one of the things we could look for in particular is something called the O2 collisionally induced absorption, or the O4 molecule. And the O4 molecule in the visible actually produces some extremely strong signatures. So this is a model of one of our self-consistent Proxima Centauris. This is an oxygen-rich, lost in ocean planet, but you can see that the very strong O4 bands distinguish it from a more Earth-like planet orbiting this particular star. So these are particular wavelengths of things that we would like to look out for. Also, if this is an ocean-lost planet, strong oxygen but no water, water is weak or missing, and it doesn't have methane as well in its environment. So, finishing up my crazy ideas for Starshot. So the first one is actually not at all crazy, which is to look before you leap. So try to characterize the planet and star from the ground in space first, and this is, of course, extremely important for target selection. We want to make sure we're going to the planet that has the highest probability of having life on it. That's something we should definitely do. For images, if we can send multiple spacecraft, that means I can get spatially, temporally, and phase-resolved images of the planet just by simply sending spacecraft with time intervals and catching the planet at different points in its orbit. I would like to be able to observe on approach and leaving if possible, and I think we're going to need some kind of telescopic capability to take data further out, since we're going to have, I think Phil said, about 40 minutes in the system itself. So we do need to observe farther out. Can we tell the size? I was talking with with Renee yesterday and saying, can we change the sort of angle of approach? Could we maybe like get a transit for this thing? He's saying, no, too much energy required. But anyway, I'll keep my mind open. What we really want, of course, is that family portrait. How many other planets are there in the system, and where are their positions, and so on. If we can get images between the water bands, between 0.8 and 1.1 microns, we can look for that glint from an ocean. And if we can get time-dependent, spatially resolved images of the planet, and even if they're not spatially resolved, we can do that mapping, which Svetlana talked about yesterday as well. So we can look for inhomogeneities on the planet, map continents, and potentially oceans. And if we could get those spatially resolved near-infrared or thermal images, we could look for temperature anomalies that might indicate geological activity and also help us get a measure of the climate of the planet. So spectra, if I could get low res with the GRISM, and it almost sounded like that was possible, which would be super awesome, then being able to get sort of phase and time-dependent vis to near-infrared spectra to look at these particular molecules in a terrestrial planetary atmosphere. These tell us about whether there's potentially life there or whether there's false positives for life. And they also provide us senses of greenhouse gases, which helps us try and figure out what the surface environment of the planet is like. I didn't talk about this, but if we can get the collisionally induced absorption and the single oxygen monomer, as it's called, we can in fact use those ratios to try and determine surface pressure. That's if it has an oxygen-dominated atmosphere. So all of these gases would be extremely important for trying to figure out what's going on there. And of course, a mapping spectrometer would be the best of all, where we could actually drift scan backwards and forwards across the planet and get, for every single pixel on the planet, we would have spectral information. That is the most powerful data set we could have. And I can, of course, have that as a dream, because this is a long way off. As we get closer to it, my hopes will be dashed, I'm sure. So physics, and I think other people are going to talk about this in this session, but just to say briefly, if we get a mass from some kind of deflection, or if we go into orbit, as Renee suggests, maybe that would help us figure out what's going on there. Or just some very simple electricity and magnetism sensors, basically to measure magnetic fields or solar winds, although I would caution, as a planetary astronomer, if we're actually in the ecliptic, that seems like a very dangerous place for us to be. And so I think we would have to look at whether we would obliterate our spacecraft by doing that. So that's basically my summary. It's not just me. I want to thank the team that has worked on all of this, the Virtual Planetary Laboratory, and I will open now for questions.
Questions, two questions. Dimitar.
So which is your favorite?
Which is my favorite what? Of these? Oh, definitely the spectral mapping. Those Venus images I showed you, that was spectral mapping. I've been in love with spectral mapping for a long, long time.
That can be done with the multiple spacecraft, not just one scanning.
Yes, that's right. So if we have multiple spacecraft, we have the temporal phase, angular type resolution. I think that would be super valuable, not just one shot. Yeah. Sorry, Phil?
Another question? Jim?
Oh, Jim.
You mentioned that WFIRST can't be used to see the glint, presumably even with the shade. Can WFIRST, since it's launching within about 7 years, is there anything else it can do to aid in it? Because it's going to be there. It's the next one after the Webb.
Right, so WFIRST, and correct me if anybody's here on WFIRST, but I think it's principally going to do the Jovians and the Neptunian type objects. Its ability to get the inner working angle, especially for an object like Proxima Centauri, that's not going to be possible with that small aperture telescope. So you need a very large aperture telescope to be able to separate out. As I said, even for Le Voir at 16 meters, we would still have to achieve 1.5 lambda over d for some of the things that we're looking at.